right, it's 3:30, so we'll go ahead and get started. Good afternoon, everyone, and welcome to today's EOL seminar. I'm Sarah Woods, and on behalf of EOL, I'm pleased to introduce Jyong-En Miao, who also goes by Jack. Mr. Miao received his master's in atmospheric science from National Taiwan University, where he is currently pursuing his PhD. As part of his doctoral studies, he is visiting colleagues at Colorado State University through February of 2025. During his professional career, Mr. Miao has served as a weather forecaster and observer for the Central Weather Bureau and Civil Aeronautics Administration. He also serves as an assistant research fellow for the Central Weather Bureau. Mr. Miao's research has embraced the dynamics and thermodynamics of afternoon thunderstorms over Taipei Basin and has involved both modeling and S-Pol radar observations from the TAHOPE and PRECIP field observational periods. His work has earned him both an Outstanding Paper Award from the Meteorological Society of the ROC and a First Place Award for the APEC Typhoon Symposium Student Competition. Please join me in welcoming Mr. Miao for his seminar titled Microphysical and Kinematical Characteristics of Merged and Isolated Convective Cells over the complex terrain of the Taipei Basin. Mr. Miao.
Thanks for the introduction. I am Jyong-En Miao, a PhD candidate at National Taiwan University. And currently, I am visiting Professor Christian Rasmussen at CSU, thanks to the study abroad program of NSTC Taiwan. And today, my talk will focus on using S-Pol observations and wolf simulation to investigate the thunderstorm dynamics and microphysics in PRECIP IOP 2. First, I would like to show some social impact of afternoon thunderstorm. So, severe afternoon thunderstorm sometimes can lead to very intense rainfall. For example, higher than 100 millimeter per hour. And this can cause severe property damage and traffic hazard. For example, the picture shows that you can see the roads because of the flash flooding. The road at Taipei City become a river. And this figure shows sometimes at airport, because of the lightning associated with severe thunderstorm, it can lead to the air traffic hazard and delay. Another thing I want to point out is that in the mountainous region, sometimes these short duration rainfall can lead to the sudden rise in water levels, which can be very dangerous and cause loss of human lives. And okay, so today's talk will focus on this multi-scale interaction contributed to orographic extreme rainfall. And so there are multi-interaction of various processes. For example, the large-scale wind, local circulation, microphysics, corporal dynamics, and terrain effect. And some studies suggest that convective cell merger can intensify afternoon thunderstorm and the associated rainfall. However, our understanding of the microphysical processes leading to the extreme rainfall is still far from complete. So it's important to investigate these features. Okay, so first you can see this terrain map shows, you can see the terrain map of Taipei Basin. And it shows that many coastal terrains over here. So this is very important because this kind of terrain geometry, it can have interaction of sea breeze and other local circulation and terrain. So which can be this kind of so investigating extreme rainfall over Taipei Basin can be beneficial to other regions with similar environment and terrain geometry. So you can see that the sea breeze from Danshui River Valley and the Keelung River Valley over here penetrate into Taipei Basin and converge at the southern part of Taipei City. So thunderstorm is likely to initiate and enhance at the southern part of Taipei Basin. So this kind of a precipitation hotspot. And some previous studies suggest that interaction between cold pools and sea breeze can be very important to the thunderstorm development. And my previous work used a sub-kilometer wave simulation nesting down to 500 meters. And the key point is that the first part of our study identified the physical mechanism of cell merger. So the key point is that there are rear-end collision and head-on collision. And the rear-end collision is due to the different cell propagation speed. And the head-on collision is the colliding cold pools. And this head-on collision is connected to the subsequent development of thunderstorm over Taipei Basin. And this conceptual diagram is based on our numerical experiment results. So the key point is that when the sea breeze penetrates into Taipei Basin, because of channel effect, it intensifies the sea breeze and associated moisture flux. And when this it further penetrates into Taipei Basin and encounter the cold pool produced by previous rainfall over mountainous region, so it enhances low-level convergence. So the key is here, the depth of cold pool should be larger than the LFC, so the cape can be released effectively and leading to the subsequent development of convection. So in summary, sea breeze and cold pool play an important role in the initiation and development of weakly forced afternoon thunderstorm over Taipei Basin. How about the impacts of terrain? So this figure is from Wu et al. 2021. They use observation and the IBM VGS. This is a data assimilation system. So they conduct this kind of terrain sensitivity experiment. So in the control run, you can see the rainfall maxima is occur within the Taipei Basin, as the cursor shows. However, when in the absence of the terrain, you can see the rainfall maxima shift outside of Taipei Basin and it weaken. So their studies suggest that terrain can intend and intensify the rainfall inside the basin terrain. Okay, and our previous study also investigated the impact of mid-level moisture and terrain on the thunderstorm evolution. So this is the three-dimensional forward trajectory. And we use the NCAR software Vapor to have this nice three-dimensional trajectory movie. So we placed 200 air parcels at the low levels just north of the gas front. And so you can see that when there is dry mid-level air, you can see this parcel can rise above to at the upper level. And the isosurface here shows this is the graupel. So this is associated with a large amount of graupel. However, when there's wet mid-level air, you can see most of air parcel is remain trapped below melting level, and there is few graupel, and the convection is weaker. So this is the conceptual diagram based on our numerical experiment results. So when there is the dry mid-level air, so because there is stronger evaporation cooling and cold pool, so it can lift the moist parcel from sea breeze. And the large convection size reduce entrainment rate, so more parcel can rise above melting level and produce latent heating and enhance the buoyancy and the updraft, and leading to the extreme rainfall over Taipei Basin. However, when there's wet mid-level air, as you can see, the cold pool is too weak. So most of air parcel remain trapped below melting level. So the instability cannot be released effectively, and the convection and the rainfall is weaker. And our analysis also showed that entrainment rate could be reduced by the cold pool dynamics and the widening of convection area. And we also conduct a terrain sensitivity experiment, and we found that the impact of terrain can modify the response of convection to mid-level relative humidity. So it is very interesting. So we called it basin confinement effect. And this basin confinement effect may be crucial for short duration rainfall extreme over complex terrain. So in summary, mid-level moisture content and terrain play an important role in the evolution of weakly forced afternoon thunderstorm. Okay, so the left figure is from Zhong and Zhou 2023. So you can see this intensity duration framework. So this is 5 years statistics of heavy rainfall over in northern Taiwan. And so my previous research work on this 14 June 2015 case. So you can see this afternoon thunderstorm case has very high intensity or very high rainfall intensity. And its duration is longer than the median value. And you also know that this case, its intensity can higher than some of the typhoon cases. So, regarding on the PRECIP field campaign, the science goal of it, you can see this intensity duration framework. So the scientific question is that in a moisture-rich environment, what is the key ingredients and processes leading to extreme rainfall in a moisture-rich environment, such as Taiwan? So my research focus on the afternoon thunderstorm is over here, the deep convection region. So aligns with the PRECIP scientific goal. Okay, so however, previous study focused on the weakly forced afternoon thunderstorm. And we know that in different environments, mesoscale processes may vary accordingly. Another thing is that the impact of terrain may be different under weak and strong synaptic environment. So it is important to know, investigate the ingredients and mechanism for orographic extreme rainfall in a strongly forced afternoon thunderstorm. So this is the surface made in PRECIP IOP2. So you can see the frontal system is over here as the cursor shows. So it's near the northern coast of Taiwan. And so we know that there are many good cases of afternoon thunderstorm in PRECIP. Why IOP2? So look at that figure. You'll find this is the radar QPE. So this is in IOP2, and the right figures is the Wolf ensemble. There are 20 members. However, none of the ensemble members will capture the extreme rainfall over Taipei Basin in IOP2. So it is important to investigate this kind of mechanism leading to orographic extreme rainfall. So the part one of my talk today is the microphysical and kinematical characteristic of merged and isolated convective cell over the Taipei Basin. And this figure shows the instrumentation. So you can see NCAR S-Pol over here, and here's the Wufenshan radar and the Shulin radar. And this shows the Banqiao sounding station. So we use S-Pol polarimetric observation data, especially the RHI scans, to investigate the microphysical characteristic of within afternoon thunderstorm. This kind of RHI data can provide valuable insight into the microphysical processes. And we also employ the samurai terrain to have the multi-Doppler wind data over the complex terrain. And we use the 3 radars to have this multi-Doppler wind, S-Pol, Wufenshan, and Shulin radars. So this is the overview of the PRECIP IOP2. So you can see from the left movie, you can see the radar image and the visible image. So you can see there is a weak rainfall occur in the morning and a strong convection, afternoon thunderstorm in the afternoon. And there is also deep convection near the northeastern coast. So the right figure shows the the rainfall map. And in this study, we focus on the extreme rainfall in the northern Taiwan, as the cursor shows, especially this heavy rainfall over the mountainous region here. And the rainfall maxima is about 150 millimeter in 3 hours. And this shows the synaptic condition. So you can see the surface front is near the northern coast of Taiwan, and the southwesterly wind prevail between 850 and 500 millibar. And from this, you can see the subtropical high. The ridge extends to Basin Channel and South China Sea. And at the upper levels, you can see this wind diffluence pattern, which is conducive to upper level divergence. Okay, so in this IOP, we have intense sounding release. So it means that we have bunch out sounding data every 3 hours. So this shows the bunch out sounding data at 8 o'clock local time. So first of all, you can see the mid-level is pretty wet. And the wind field within the boundary layer is pretty weak. And there is southwesterly between 800 and 500 millibar. 3 hours later, you can see at the low levels, you can see the northerly below the 950 millibar, which indicate the sea breeze penetrate into the Taipei Basin. And the Cape also increased to 2,600 joule per kilogram. And okay, so this shows the spatial and temporal distribution of S-Pol reflectivity greater than 40 dBz. So basically this is 5-hour statistics. So you can see that from the figure A, the strong convection mainly occurred over the Snow Mountain Range. And then from the figure B, the half-molar diagram along southwest to northeast direction, you can see there are 2 episodes of strong convection. The episode 1 occurred at 12 to 14 local time. Episode 2 occurred at 15 to 17 local time. And the figure C shows the half-molar diagram along northwest to southeast direction. So it is clear that the strong convection was confined within the mountainous region, resulting in heavy rainfall over Snow Mountain Range. Okay, so now we have identified 2 episodes of strong convection. So now we can look at the convection evolution during episode 1. So the color field is the S-Pol reflectivity, and the arrow is the multi-Doppler wind at 1.5 kilometer height. First of all, you notice that there is a multiple cell merger event. And regarding on the mechanism of A and B merger, you can see that the southwesterly is stronger near the cell A. And so the A and B merger may be due to the rear-end collision due to the different cell propagation speed. And after the merger of A plus B and C, you can see this kind of enhanced low-level convergence produced by upslope winds. And these features prevail. And then cell A plus B merge with C and intensify. So it suggests that terrain may play an important role in the merger of cell A plus B and C. Okay, so next we look at the evolution of convection during episode 2. So you can see that the convection during episode 2 is much weaker than episode 1, and they are isolated convective cells. Another thing is that you can see this kind of, interestingly, you can see this kind of a cyclonic rotation here, as the cursor shows, near the Yilan County. And this mesoscale vortex moves northward gradually, and the easterly wind north of this vortex penetrate into the Snow Mountain Range. So you can see produce some convection over Snow Mountain Range here. And then this convection weaken gradually. Okay, so now because we have this valuable S-Pol RHI data, and very luckily, the S-Pol 78-degree RHI capture the cell merger process of A plus B and C, so we can have these polarimetric observations of cell merger. So this time is the before cell merger. So you can see from the ZH plot, the echo top is about 14.5 kilometer, and the PID shows that the graupel is located at 5 to 10 kilometer height. And the ZDR plus shows the ZDR columns here, as the cursor shows, and here, which indicate the convective updrafts. And if you look at it carefully, you can find some shallow cumulus cloud between these two convective cells, which is associated with the low-level convergence produced by the upslope wind. And 12 minutes later, you can see this shallow cumulus cloud develop and extend above 8 kilometer height. Another 12 minutes later, you can see the cell A plus B merge with cell C and produce the enlarged vertical extent and horizontal extent of strong convection. And the ZDR plot shows that you can see it seems like its morphology transition from the discrete columns into the ZDR, a crown-like structure. So this kind of feature, if you look at the enhanced ZDR region, 1 dB, it looks like a crown rather than a column. So we call it ZDR crown. And the KDP plus shows that the KDP column height is maximized about 7 kilometers. And the maximum value of KDP was larger after cell merger. Okay, 12 minutes later, you can see the convection still intensify, and the echo top is exceeding 16 kilometers. And there is a maximum ZH is about 60 dBz. So, and the ZDR plot, also this kind of ZDR crown signature also maintained. And from the PID, it shows that you can see that the water-coated hailstone and large supercool raindrop, which produce high value of KDP above the melting level. And so if you look at it carefully, you can find the ZDR part, there is some high value of ZDR here, as the cursor shows, below the position of graupel and hill. So this high value of ZDR may be due to the shading of melting of graupel and hill, which is connected to the heavy rainfall near the ground. Okay, so now we have the polarimetric RHI observation of the cell merger process. Next, we look at the kinematic structure during merger process. So this vertical cross-section, the position is the same as the S-Pol 78-degree RHI. So you can compare, match well with the S-Pol observations. For example, okay, first the color is the vertical velocity, and the blue contour is 35 dBz ZH. So before cell merger, you can see, first of all, the retrieve updraft here and here match well with the ZDR columns. And there is also upper motion between these two convective cells, which is associated with the upslope wind convergence. And the maximum vertical velocity before the merger is about 12 meters per second. And after the multiple cell merger, you can find the upper level updraft also merge together and intensify to 22 meters per second, which is associated with a large amount of graupel and hill, which is shown before. Okay, so this shows the S-Pol 83-degree RHI during episode 2. So you can find that this convective cell become shorter and isolated. The echo top is about 12 kilometers. And there is no ZDR crown during episode 2. And only there is barely well-defined ZDR column in episode 2. And from the PID plot shows that you can see instead of graupel particles, there are a large amount of dry snow at the upper levels and wet snow near the melting level. And the area of heavy rainfall shows that the rainfall intensity decreased in episode 2. So next we look at the kinematic structure during episode 2. So first of all, there is no sail merger and updraft merger in episode 2. And the updraft structure, it seems like it shows a disorganized and slantwise structure with a maximum vertical velocity of 8 meters per second. And if you look at it carefully, you can find this easterly flow, which I mentioned before is north of the mesoscale vortex. The easterly wind north of the mesoscale vortex penetrate into snow mountain range. So this kind of, it is clear that it is pretty shallow. It's below 2 kilometer height. And this easterly flow advances westward gradually, as this box shows. So, okay, so previous studies suggest that tracking ZDR column heights and area can be beneficial to nowcasting severe weather. For example, this figure is from Custer et al. 2019, and shows that you can see the severe storm has a larger ZDR column size, the area, and a higher ZDR column height. So we want to investigate this, the relationship between ZDR column metrics and the updraft properties in over Taipei Basin. So we use the TAHOPE. This is a Python package for objectively tracking the object. And so we use TAHOPE to tracking ZDR columns and on the RHI coordinate. So we are trying to take advantage of the high resolution RHI data and then quantify the ZDR column metrics. And the definition of ZDR column is that follow the previous study is greater than 1 dB and extending up to the 5 kilometer height, which is the melting level, the height of melting level in the summer of Taiwan. So you can see the upper panel shows the maximum height of ZDR column. So you can see before cell merger of A plus B and C, the maximum height is about 6.5 kilometers. And around the merging time, it increased to its maxima to 7 kilometers, which indicates the intensifying updraft, which can bring more supercooled droplets to the above the melting level and produce high value of ZDR. And the lower panel shows that the maximum width of ZDR column. So you can see that before the merger, the ZDR column width is about 4 kilometers. And around the merging time, it increased twofold to 8 kilometers, and then further increased to 13 kilometers. Oh, in this study, we define ZDR crown as a special case of ZDR column with a 5 kilometer height width greater than 8 kilometers. So you can see this ZDR crown signature maintained for about 30 minutes, which may be a manifestation of updraft merger. And this kind of feature is less emphasized in the previous studies. Okay, so this shows the evolution of objects during episode 1 and 2. And so first we look at the left panel, which shows the updraft vertical maximum velocity and the area during episode 1. So you can see that the updraft velocity and area rose rapidly around the merging time. And it seems like the updraft velocity and area follow a similar evolution of ZDR column width or ZDR crown. And when the updraft enlarge, it means that the updraft core is less likely to invaded by the environmental dry air, and so it can maintain its buoyancy and intensity. And how about the episode 2? So the scale is, the right panel shows the object matrix during episode 2. The scale is the same as the left panel. So it is clear that the object velocity and area is pretty weak in episode 2. And there is no ZDR crown in episode 2. So next, we look at the evolution of microphysical process during episode 1. So this is the CFET of ZH, ZDR, and KDP. And the first row shows before the cell merger, and the second row is after the cell merger. So if you look at the, for example, the ZH plus 35 dB ZH, you can see the height increase to 12 kilometer height, which indicate the more intense convection. And the ZDR plus shows that the height increased to 6 kilometer, indicate a stronger updraft. We can bring more supercooled droplets above melting level and produce high value of ZDR. Another thing is that, interestingly, you can see this kind of feature at the upper levels. You can see this downward decrease of ZDR between 8 and 12 kilometer, which indicate more active rhyming process after the cell merger. And there is another feature is that there is downward increase of ZDR near the melting level was more pronounced after cell merger, and this indicate the more graupel melting, which is connected to the heavy rainfall near the ground. Okay, so this shows the CFET during episode 2. So you can see that the evolution of convection is weakening. First, for example, you look at the 35 dB ZH, the height decreased to 7 kilometer. And the ZDR plus shows the height of ZDR is 5 kilometer or even lower, which means it has a much weaker updraft during episode 2. And at the upper levels, the main distribution of ZDR approach 0 dB, indicate no active rhyming process in episode 2. And the black line shows the average of this, the average profile. So it shows that there is smaller raindrop and lower rainwater content in episode 2. Okay, so we also use the microphysical fingerprint technique to investigate the one-rain process. And the left figure is episode 1, right figure episode 2. So this is the phase diagram of this method is proposed by Convective et al. And this shows the phase diagram of ZH and ZDR changes over the strong convection areas, which means it's greater than 40 dBz. And we do the average in two framework, the Eulerian and Lagrangian framework. So when I say Lagrangian framework or semi-Lagrangian framework, I mean we track the maximal connected area of the strong reflectivity region over time and do the average. So the left figure shows that during episode 1, there is a distinct pathway. So the color is represent the radar, S-Pol radar observed time. So it shows that there is a distinct pathway from coalescence to the evaporation and side sorting region. However, during episode 2, you can see most of the sample are located in the evaporation region, which suggests that the dominant one-rain process are different between these two episodes. And how about we can compare with other oceanic convection cases? So the Dynamo data set, which also use S-Pol radar data, and this is from the study of Convective and Pratt 2014. Their study suggests that, indicate that convection, in the convection cases, the dominant one-rain process are coalescence and evaporation. And in the stratiform case, the dominant processes are breakup, coalescence, and evaporation. And our study on this terrain-confined afternoon thunderstorm in PRECIP IOP2 also shows coalescence and evaporation is a dominant warming process, which consistent with their results on oceanic convection. And if you change this phase diagram, the x-axis, to initial ZDR, so I mean the initial ZDR is the ZDR at the top layer, so it means a 3 kilometer height. So you will find that, okay, the left figure shows episode 1, and right figure episode 2. So you will find that initially smaller droplets, which means smaller initial ZDR, result in larger ZDR increase. So you can see this kind of relationship in these two episodes. However, when you combine the samples from these two episodes, so when it's combined together, this kind of relationship become obscure, which suggests that convection organization may impact the evolution of drop size distribution. Okay, and this is the take-home message. And okay, our study shows that the multiple cell merger favored by the upslope wind convergence led to intense and broadening updraft and extreme rainfall over Taipei Basin. And a unique radar signature, ZDR crown signature, which is associated with the peak phase of the storm and indicating broadening and intensifying updraft. And the radar observations like ZDR crown signature could be crucial for predicting severe weather over complex terrain. And this is the part 2 of our study. So as I mentioned before, the impact of terrain may be different under weak and strong synaptic environment. So in this study, we aim to investigate the impact of terrain on the strongly forced afternoon thunderstorm in PRECIP IOP2. And we employ high-resolution WRF simulations to conduct these terrain modification experiments. So the finest grid spacing is 1.5 kilometer. And you can see these half terrain run, which reduce the Taiwan terrain height to half. And the no terrain run reduce the Taiwan terrain height to 0. And no terrain water run reduce terrain height to 0 and change the land max of Taiwan to water. So this is just preliminary results. So this shows the half-model diagram of reflectivity. So first of all, you can see in control run, there are 2 episodes of strong convection, which is similar with the observations. And in half-terrain run, you can see it become disorganized. And in no-terrain run, it becomes even more short-lived. And the no-terrain water run shows that even the surface friction may have some impact on the convection evolution. And this shows the potential vorticity at 1.5 kilometer height. So, so you can see this vortex dipole as the cursor shows over here and here, which is produced by terrain. So you can see this negative PV over northwestern Taiwan and positive PV over southeastern Taiwan and the ocean, as the cursor shows. And this is produced by the horizontal wind shear. So it's wind shear vorticity. And in the half-terrain run, you can see this vortex dipole weaken. And in no-terrain run, this vortex dipole disappear. And this vortex structure may impact the evolution of convection in IOP2. And this shows the difference of low-level wind shear between different runs. So, for example, that figure shows the half-terrain run, the difference between half-terrain run and control run. And it shows that when reduce the Taiwan terrain, it increased the low-level wind shear at the windward side and decreased the wind shear at the lee side. And this kind of pattern become more significant in the no-terrain run, as the cursor shows. And the difference between no-terrain water and no-terrain run shows that you can see the wind shear, low-level wind shear decrease over the Taiwan land. So this kind of wind shear difference may impact the subsequent convective organization, which will be the one of the topic of my future work. Another thing is that in this study, we aim to quantify the influence of terrain and frontal system forcing on the thunderstorm. And another thing is that, as I mentioned before, previous study focused on the afternoon the impact of terrain on the weakly forced afternoon thunderstorm. And in PRECIP IOP2, we this study about the strongly forced afternoon thunderstorm. So we can compare the impact of terrain on convective development in strongly forced versus weakly forced afternoon thunderstorm cases. Okay, and this is the implications. So in our observational study, we proposed the ZDR crown signature, which may be a manifestation of updraft merger. And there is also emergent study in the US investigating the relationship between ZDR current size and the severe weather. And they found a positive correlation. So given the occurrence of this kind of feature, the ZDR crown or larger ZDR current size in severe storm, this phenomena may be common in the intense convection across different regions, but require further study. And our preliminary results of modeling study shows that the impact of terrain on strongly forced afternoon thunderstorm. Actually, it appears to that the impact of terrain is different between the weak and strong synaptic condition. So this kind of information could be beneficial to other regions with similar environment and terrain configurations. Okay, so finally, combined with our observational and modeling study, we identify the key ingredients and process in the extreme rainfall event in a moisture-rich environment. And the science goal of PRECIP is this. And under the global warming scenario, we know that the moisture content will increase based on the Clausius equation. So it is important to know the key ingredients and mechanism in the extreme rainfall event in different moisture content environment. And our study contribute to the key ingredients in extreme rainfall in the moisture-rich environment, which aligns with the PRECIP science goal. Okay, that's all I have. Thank you very much.
Thanks for that very interesting talk. Quick reminder for those of you online, enter your questions in Slido at the bottom of the screen. Do we have any in-room questions?
Thank you very much. That was an excellent presentation, a very interesting study. My question is if you've had a chance to look at any of the MPD water vapor LiDAR data. There were 3 profiling systems that, give,
Thanks for the questions. And yeah, the MPD will provide valuable information about the low-level moisture. We haven't looked at it, but I think I will look at it in the future. Thank you so much.
Yeah, thank you. Yeah, during the PRECIP, you're not going to have any of the MPD data. It will be severely attenuated by the rain. But prior to the storms, there might be some interesting observations that you could look at, in particular to look at the differences in the mid-level moisture.
Yeah, you will be very interesting to look at it. Thank you.
Thanks, Tammy. Any other questions in the room?
Thank you for your presentation. So you mentioned that the low level moisture is one of the key ingredients to the convective event.
Yeah.
Have you performed a sensitivity study on what may be the minimum threshold of moisture that's required to trigger this type of convection?
Okay, thanks for the questions. And okay, our previous study investigate the impact of mid-level moisture. And so it shows that the thunderstorm evolution is impacted by the mid-level relative humidity. And however, we haven't looked at haven't do the sensitivity experiment about the low-level moisture. But I think it will be a very important topic to investigate in the future. Thank you.
No questions online. Any others burning in the room?
I enjoyed your talk. I liked the PV diagram towards the end too. Do you have any sense for what effect that PV has on the organization of convection, kind of on the lee side of Taiwan?
Yeah. Okay, thanks for the questions. And as you can see, this kind of, as I mentioned before, there's a mesoscale vortex near the northeastern coast. And this kind of, the easterly wind north of this vortex penetrate into storm range. So it kind of prolong the duration of this rainfall event. But we are trying to look at what is the origin of this mesoscale vortex. So if you look at it carefully, because although it is pre-convection environment for the afternoon thunderstorm over Taipei Basin, however, actually there is rainfall over here because there is a perturbation system over as the cursor shows. So, and you can see there is basically there are positive PV over here. So it seems like this mesoscale vortex embedded in this positive PV environment. So we are trying to look at the origin of this mesoscale vortex.
It kind of looks like it's coming from the train. It kind of looks like it's coming from the train on the upwind side, as you'd expect from a curl of friction.
Yeah, thank you so much.
Any other follow-up? All right. Well, with that, we'll go ahead and thank our speaker for that very interesting seminar. I learned some new stuff about radar today, so thank you very much.
Thank you.